Hello, my name is Paul Geyer, and I'm here to chat with you today about activated sludge wastewater treatment plants. Here's what I'll be talking about today. Some introductory remarks, activated sludge processes, closed-looped reactor design criteria, some example calculations, and then some references in bibliography that will be helpful to you moving forward. This, by way of introduction, is just a little bit about me and what I've been doing for the last few decades. The activated sludge process has been employed extensively throughout the world in its conventional form and modified forms, all of which are capable of meeting secondary treatment effluent limits. This publication presents the different modifications of the conventional activated sludge process, including general bases for design, methods of aeration, and design factors for aeration tanks, final sedimentation units, and sludge handling systems. Figures 1 through 4 are schematic diagrams of the conventional and modified processes. The characteristics and obtainable removal efficiencies for these processes are listed in Table 3. All designed processes will include preliminary treatment consisting of bar screen as a minimum and as needed, comminutor, grit chamber, and oil and grease removal units. In a conventional plug flow activated sludge plant, Figure 1, the primary treated wastewater and acclimated microorganisms, activated sludge or biomass, are aerated in a basin or tank. After a sufficient aeration period, the flocculant activated sludge solids are separated from the wastewater in a secondary clarifier. The clarified wastewater flows forward for further treatment or discharge. A portion of the clarifier underflow sludge is returned to the aeration basin for mixing with the primary treated influent to the basin, and the remaining sludge is wasted to the sludge handling portion of the treatment plant. The portion recirculated is determined on the basis of the ratio of mixed liquor volatile suspended solids, abbreviated MLVSS, to influent wastewater biochemical oxygen demand, which will produce the maximum removal of organic material from the wastewater. Recirculation varies from 25 to 50% of the raw wastewater flow depending on treatment conditions and wastewater characteristics. Figure 1 indicates the conventional plug flow activated sludge flow process. In this process, step aeration, the influent wastewater is introduced at various points along the length of the aeration tank. Sludge return varies between 25 and 50%. Aeration, or the oxygen requirement during step aeration, 3 to 7 hours, is about half that required for the conventional process. This results from a more effective biomass utilization in the aeration basin, allowing organic loadings of 30 to 50 pounds biochemical oxygen demand per 1,000 cubic feet per day as compared to loadings of 30 to 40 pounds biochemical oxygen demand per 1,000 cubic feet per day permitted for conventional systems. Figure 2 is a schematic diagram of the step aeration flow diagram. In the contact stabilization process, the contact stabilization is characterized by a two-step aeration system as indicated in Figure 3. Aeration of short duration, 1/2 to 2 hours, is provided in the contact tank where raw or primary settled wastewater is mixed with the activated sludge in the contact tank. The effluent from the contact tank is then settled in a final settling tank. The settled activated sludge to be recycled from the final clarifier is drawn to a separate re-aeration in a stabilization basin for 3 to 8 hours of aeration time. It is then returned to the contact aeration basin for mixing with the incoming raw wastewater or primary settled effluent. In addition to a shorter wastewater aeration time, the contact stabilization process has the advantage of being able to handle greater shock and toxic loadings than conventional systems because of the buffering capacity of the biomass in the stabilization tank. During these times of abnormal loadings, most of the activated sludge is isolated from the mainstream of the plant flow. Contact stabilization plants will not be used where daily variations in hydraulic or organic loadings routinely exceed a ratio of 3 to 1 on consecutive days, or for plants with average flows less than 0.1 million gallons per day without approval, prior approval of the owner. Table 3 is a schematic diagram of the contact stabilization process flow. For the completely mixed activated sludge in the completely mixed process, which is illustrated in figure 4, influent wastewater and the recycled sludge are introduced uniformly through the aeration tank. This allows for uniform oxygen demand throughout the aeration tank and adds operational stability when treating shock loads. Aeration time ranges from 3 to 6 hours. Recirculation ratios in a completely mixed system will range from 50 to 150%. Figure 4 is a schematic diagram of the completely mixed process flow. With extended aeration systems, extended aeration activated sludge plants are designed to provide a 24-hour aeration period for low organic loadings of less than 20 pounds biochemical oxygen demand per 1,000 cubic feet of aeration tank volume. This approach, which can be used for treatment plants of less than 0.1 million gallons per day capacity, reduces the amount of sludge being wasted for disposal. With regard to the oxygen ditch approach, the closed-looped reactor, also known as an oxygen ditch and illustrated in figure 5, is a form of the extended aeration process. The wastewater is propelled around an oval racetrack configured basin by mechanical aerator mixing devices located at one or more points along the basin. These devices can be either brush aerators, surface aerators, or jet aerators. The velocity in the basin is designed to be between 0.8 and 1.2 feet per second. The closed-loop reactor is the preferred type of activated sludge system for many installations. Figure 5 is a schematic diagram of a closed-loop reactor treatment process. Table 1 presents the design criteria to be used for the design of a closed-loop reactor plant. With regard to the aeration tank design, all oxidation ditch plants use looped channels or ditches. A looped channel with a partition in the middle may be shaped like an oval or a concentric ring. The design engineer may adopt a specific channel configuration and flow scheme recommended by the equipment manufacturer or supplier. The number of loops and the channel depth are dependent upon the size of the plant. A shallow channel, less than 14 feet deep, is used for smaller plants with unlimited land area available. A deep channel, greater than 20 feet, should be designed for larger plants or to conserve heat. Multiple channel or multiple loop is the preferred design so that part of the plant can be shut down for repair and maintenance. A drain should be provided for each channel. This provision allows mixed liquor or accumulated grit material to be drained from the channel without expensive pumping. Many oxidation ditch plants do not have drains in their channels and are having maintenance problems. Deep channels are to be built exclusively with reinforced concrete. A concrete liner can be placed against the earth backing in shallow channels by pouring concrete or gunite, shotcrete, to a thickness of 3 to 4 inches. The concrete or gunite should provide a minimum compressive strength of 3,000 pounds per square inch in 28 days. Depending on the width and depth of the channel, various types of aerators can meet the oxygenation and mixing requirements. One type is the rotor aerator, which is a horizontal shaft with protruding blades which rotate, thereby transferring oxygen into the wastewater and propelling it around the ditch. Figure 6 illustrates a typical horizontal shaft aerator. The minimum length of shaft is 3 feet, the maximum length is 30 feet. This type of aerator is suitable for shallow channels. The induction aerator, this type of aerator, which is available in various sizes, draws the mixed liquor and air down a U-tube and discharges it for a distance downstream in the channel. The compressed air at low pressure can be injected near the top of the downdraft tube to enhance oxygenation. A bulkhead, which should be partially opened at the bottom, is required to separate the channel to maintain the flow circulation. This type of aerator is suitable for shallow to moderately deep channels. Jet aeration is specifically designed for deep channels. Both air and the mixed liquor are pressurized by aspirator pumping into a mixing chamber from where the mixture is discharged as a jet stream into the surrounding channel liquid. Deep channels are used to take advantage of better oxygen transfer. Figure 7 illustrates a jet aerator among various other types of aerators. Figure 6 is an illustration of a typical horizontal shaft aerator configuration. Figure 7 indicates various types of aerators. With diffused aeration plus slow mixer, this type of aeration is more suitable for deep channels. Air bubbles are introduced into the mixed liquor through a pipe grid system with diffusers to provide oxygenation, while a slow propeller mixer provides the flow circulation and mixing. Aerators should be sized to provide adequate mixing and oxygenation. However, the same size rotor provides different levels of mixing and oxygenation depending on the degree of its submergence. First, the oxygen requirement must be calculated for a level that will satisfy its carbonaceous biochemical oxygen demand removal, as well as nitrification, denitrification if needed. Oxidation ditch equipment manufacturers provide tables or charts for selecting the aerator size for any given speed and submergence immersion based on the calculated oxygen requirement. The aerator size should also be checked against the mixing requirements set by the manufacturers. Preferably more than one aerator should be used per channel. They should be placed at different locations so that if one breaks, the channel will still function. The procedure for selecting the jet aerator size is similar, except there is no submergence factor. The sizing of the induction aerator and the diffused air plus slow mixer units is not precise. Design data for these new aeration systems are not yet available. One reason for this is that the amount of energy required for mixing relative to the energy required for oxygenation is uncertain, since it depends a great deal on the channel geometry, which varies among plants. More testing data must be collected before a design criterion can be established. With regard to sludge dewatering and disposal in the closed-loop reactor design, sludge from oxidation ditch plants operating in the extended aeration mode with sludge retention times of 20 to 30 days can be wasted directly to open drying beds. It can also be wasted directly to tank trucks which spread the liquid sludge on the plant grounds or on adjacent land. The degree of sludge stabilization in the oxidation ditch is equivalent to that of a conventional activated sludge plant operated at a 10-day sludge retention time followed by aerobic digestion of the sludge for 7 to 15 days. In most climates, 1 square foot of drying bed surface area per population equivalent, 0.17 pounds biochemical oxygen demand per capita per day, should be used. This capacity can accept 2.2 cubic feet of wasted sludge per 100 capita per day, which is typical for domestic wastewater treatment. Following now are some example calculations, which we will not go through verbally here. A point that I would like to make once again is that the some of the figures and illustrations associated with these example calculations are not as clear as might be desirable, but they are the best available, and you can increase their readability by increasing the focus of your screen. This example calculation continues. Calculation of the oxygen ditch volume is illustrated on this slide. Calculation of the rotor requirements is illustrated on this slide. This figure relates rotor speed in RPM to pounds of oxygen per hour per foot of rotor. The example calculations continue on this slide. This illustration compares rotor speed to power required in kilowatts per linear foot of rotor for different immersions. The example calculations continue on this slide. And the illustrated calculations continue on this slide. And the example calculations continue. Final clarifier sizing calculations, and a check for nitrification in the oxygen ditch. The example continues. And continues on this slide. Additional calculation illustration. And this, of course, is a slide that is not as clear as it might be, but you can improve the readability by enlarging the image on your computer or whatever you're viewing this on. And the calculation continues. Summarizing the design criteria for the horizontal shaft, aerators, and a multiple ditch unit. And following here are a number of references, and there is also a bibliography included. And all of these will be of use to you in moving forward with design in this area. Environmental Protection Agency, of course, is in the forefront in this area of wastewater treatment and has a number of highly valuable process design manuals. Some non-governmental publications are available from the American Water Works Association and the Water Pollution Control Federation. And a bibliography here that will be helpful to you. And that brings us to the conclusion of this very brief discussion of activated sludge wastewater treatment plants, the basic activated sludge plant plus the variations that are available. I hope this has been of some interest to you and was about what you were looking for, and that some of the information here will help you as you move forward addressing these projects as they come across your desk in the future. With that, let me thank you once again for letting me chat with you, and have a nice rest of the day.